Hello everybody at the third EVCon, EVCon 2013. I'm Dennis.
And I'm Conrad.
We are from REAPsystems. REAPsystems is a battery systems specialist specializing on lithium-ion cell technology. We mainly started with battery management systems 10 years ago. Battery management systems, something Jack Rickard really loves, as we all know. Unfortunately, this year we can't be there. We really regret this. I'm sure you're all having a fabulous time over there. So we thought we'd send you a little video with some technical information. So today's technical session is all about these. These are high power connectors or bus bars, which are used to connect the high power lithium-ion cells with each other. And we would like to show you the impact of the cleanliness of these connections. You might think, well, we all know they should be clean, and that is of course true, but what not everyone might know is what the impact actually is if they are not clean. So how are we going to approach this? Firstly, we'll test a battery with these terminals as they come from the factory, without cleaning them. Then we'll clean them, and then we'll redo the same test after cleaning. Then we'll treat the cell terminals and the bus bars with some special grease which prevents the metal contacts from oxidizing, and then we'll redo the same test again, just in order to find out whether the grease layer actually makes the performance worse or increases the resistance. So I hope you find that interesting. A short disclaimer. These are high power batteries, so please be careful when handling and working with them or when testing them. They are lithium-ion batteries, so they can be particularly dangerous. They can catch fire if you overcharge them or over-discharge them, or if you short-circuit them, or if they get too hot. And finally, I would like to mention that we are not claiming that our approach or our test setups are the best. We'd just like to share with you how we approach things and what the setup is like, so that you could redo the same test and hopefully come up with the same result. So thanks for listening, and I hope you enjoyed. See you later. Right, so we are in front of the temperature chamber now, and Conrad is going to explain the setup a little bit here, so that you all know what we are doing here.
Okay, we are conducting our test today inside our environmental chamber here, so we have controlled conditions for comparison between the two cell connection options. Let me give you a quick description of our setup inside the chamber. We're using 4 Sky Energy 100 amp hour lithium iron phosphate cells, and these have been strapped together using luggage straps with pieces of wood on each side to clamp the cells together to prevent expansion during operation. We're using one of our slightly older BMS products here to monitor the cell voltages and temperatures during the testing, and this is connected up to the cells with fused measurement wires and temperature sensors, which we'll discuss in a moment how they're connected up. We're using the supplied laminated copper bus bars between the cells, and we also have a current sensor to measure the current, which is on the cable here. This is connected to the BMS here, and we are communicating with the BMS via a CAN bus link through the port hole in the side of the chamber to a PC housed externally.
So we thought it might be useful and worthwhile to explain shortly how the temperatures are actually measured and what we use to do this. As you can see here, we've got the temperature sensors bolted directly to the terminals, and as we said earlier, we've got 7 of them distributed around this relatively small battery. So we bolt them directly to the terminals, because that allows us to measure the temperature more inside the cells. If we were to have the thermistors or temperature measurement probes in between the cells or on the case, then it would take quite a while before the temperature from inside the cells gets to the outside of the cell. And we want to use the battery for high performance, high currents. So we are very interested in how hot it actually is inside. Basically Konrad is now going to explain how we make these thermistors.
Yes, the BMS has 7 temperature measurements, and we are using fairly common thermistors, and to get a very good thermal connection to the cell bus bar and terminal, we take a common rig terminal and bond the thermistor inside the throat using some thermally conductive adhesive.
Right, so we've seen the inside of the temperature chamber and the setup of the battery in there, and Konrad has kindly finished the whole setup. So what is this all about? You know, how does it all work? What are all these gadgets?
Okay, well, the biggest gadget we have here is our environmental chamber, which you've seen inside of already. We have our 4 cells at 28 degrees now. Through the porthole we have the high power cable which allows us to charge and discharge the battery. This is connected via this big cable here to our electronic load and our power supply here. This equipment allows us to charge the battery up to 120 amps or discharge it up to 400 amps. Today we'll be operating our discharging the load at 300 amps. The other important cable coming from the environmental chamber is this CLAN bus cable. Now we use this to communicate with the BMS, and we can monitor all of the parameters of the battery in our PC tool software here, which is showing us all the vital signs like temperature, voltage and current. So in this setup here, we also have a middleman piece of software which is controlling our electronic load and power supply. So we can enter in our software here our demand. For the test today we're requesting 300 amps for 60 seconds, then 60 seconds of rest. And that is a cyclical repeated process until the battery is empty. But the BMS via the CAN bus is also able to modulate our request to the electronic load and power supply and reduce it to keep the battery safe, be it for temperature, current or voltage.
So this means this here is telling the electronic load and the charger what to do. So that could be either a drive cycle or just a discharge or charge current. We are asking the electronic load of the charger to do to the battery, and then the BMS can interfere with that and make sure that the battery is kept safe. That's how it works.
Yes.
And then also this can log the data, and we can then later look at them and see what the results look like offline.
Okay, I'll show you now how we can clean terminals on the battery to improve the performance and how we assemble our battery modules for testing. We're using a steel bristle brush here, and this is a fairly dirty looking copper bus bar. And take your brush and really start scrubbing quite strongly, but you'll quickly see the difference on the surface there. You've removed all the tarnish. I'll clean another side. So big difference. Just to show side by side. So these are uncleaned terminals as delivered from the manufacturer, and we can see the copper here is quite tarnished, and the aluminium is not particularly clean. So I've cleaned the bus bars with our wire brush and also the cell terminals. I've applied some compound to the aluminium terminal and also some other compound to the copper terminal on the cell. I'll now take my clean bus bar, put it in position carefully, take our stainless bolts with spring washers, and apply torque to the manufacturer's recommended level, which in this case is 14 Newton meters.
Okay, so we are just about to start the test now, and the first thing we are going to do is we are starting a log on PC Tool so that we can log the data and look at them later. So how does this work?
Yes, I'm just selecting a suitable file and saving it. And this will be logging once a second cell voltages, temperatures, which you can then use to analyze later.
Okay, so can we see the graphs?
Yeah.
And so what's next? We are starting the test now, I guess, with this software here.
Yes, as before, we're testing 60 seconds of discharge at 300 amps and then rest of 60 seconds, and that is repeated. So let's start the test and see what happens.
Ramping up the current, 300 amps. Okay, so you can see the current here as well, I guess.
Yeah.
And also here on the time graph.
So we can switch back to the previous results.
Yeah, for comparison, right? Could we zoom into the current, please?
So here we have the actual current that the battery is delivering at the moment, which we can see with our cursor here. And this is our third cycle, third repetition at 300 amps.
So there's no current reduction by the BMS because the cells are still very far away from their maximum operating temperature, so the BMS sees no reason to reduce the current. Whereas previously, before we cleaned the contacts, we had to reduce current already on the second burst. So already here we were reducing, but certainly on the third. Well, we've got another 20 or so of these discharge bursts, and we're not going to show them all on video because that's going to take quite a while. So we'll get back to you as soon as the tests are finished.
Well, the test is now completed, and we've discharged the battery to 2.7 volts, and these are the results.
Right, so could you zoom in a little bit here so we can see the current graph a little bit better? See what actually happened. That's good.
Yeah.
So the first 11 discharge bursts here, we've got virtually no, or we've got no current limitation, so the temperatures are well below 45 degrees centigrade, and then we are starting to limit the current because of temperature. So how did this compare with the previous one? Could you show both screens again, maybe?
So in the original test, we achieved just 60 seconds of 300 amps completed. All the later discharges were limited due to high temperature. So this is on the previous original test, and on this last test now we've managed to do 11 complete 30 amp 300 amp discharges at 60 seconds without any temperature limitation. So it's a big improvement in the performance.
And the temperatures, the cell temperatures are now all well below 55 degrees centigrade, which is the manufacturer's recommendation. They're relatively close to each other. The ones in the middle, the cells in the middle, are warmer than the ones on the outside because they get less cooling, I guess. What else can we see? We discharged 102.5%, so 102.5 ampere hours. It's a 100 ampere hour cell, some years old. Not so bad.
So we can stop the log now and prepare it for analysis later.
Yeah, so we can overlay them later on a graph. Yeah, that would be good. So we got the results up on the screen now from the log data, and the first we can see here on the left is what is all this, Conrad? What are these things?
Well, we're showing here time, elapsed time of the test.
Time
on
at
the
the bottom.
bottom.
Right.
We have the temperature, the highest temperature being shown on the left axis, and
Yeah.
discharge current on the right axis.
Okay, and negative means discharging.
That's right, yeah. So here we're
Okay.
showing the first 10 steps of our discharge. So we have 100 seconds of 300 amps. And what we
Yeah.
see immediately is that the pack, which is uncleaned, you have almost immediate limitation in discharge current.
So this is the dotted curve here, limitation in discharge currents.
Yeah. Whereas if you have a clean module or a module which has been cleaned and greased, we're able to pull our full 300 amps for 60 seconds
Yeah.
for the first 10 cycles.
Down here.
And this actually corresponds to half of the battery capacity being discharged.
Okay, so what's happening to the temperatures then?
Well, the dotted line there, which is really jumping up very quickly, shows us the highest temperature on the uncleaned pack. So very quickly, the BMS has to respond to high temperature, and it reduces the allowable discharge current.
And this goes up to 55 here on the first 10 cycles,
That's right.
whereas on the cleaned contacts it's going up to only 45.
Yeah, so this means no limitation for the cleaned modules, and there's very little difference between the behaviour for both of those.
So what are, these two is greased and cleaned and greased and just cleaned, right?
That's right.
And there's not a big difference, which means no harm in greasing your contacts if you're using the right sort of products, and that should preserve the metal from oxidation. So what are the remaining discharge bursts looking like? Okay, so what can we see here then?
What we see here, when the contacts are clean, there is no limitation for the first 10 steps, which is approximately half of the battery capacity.
Up to here.
Yes. And then, as the temperature rises in the pack, we have a limitation due to temperature. And
here?
towards the end, we'll start limiting on voltage, which is, in our case, 2.7 volts.
This final bit here.
That's correct, yes. The results for the grease terminals is identical.
Okay, so no difference between cleaning and greasing.
That's right.
Okay.
For this test, we've configured the BMS to start limiting at 45 degrees.
Which is around here.
Yes, and that is to balance performance against life of battery. Manufacturer recommendation is 55 degrees C, so we could increase that temperature to gain longer performance.
So if we had increased to 55, we would have elongated the full performance time, potentially, for the whole discharge.
Potentially, yes. Yeah. And if we look at the results without any cleaning, we see there's an immediate reduction, limitation in the discharge current.
Which is this here.
Yeah. And we really can't extract much power from the battery due to the high temperature, and which means we have a much longer time to discharge the battery fully.
It's this bit here. Okay, so why do we get these spikes down here? What are they?
Well, the BMS always allows you to pull initial high current for acceleration purpose, but then it limits the discharge for temperature.
Okay, that's interesting. So, what are the temperatures doing across the test? this shows the temperatures, the behavior of the temperatures quite nicely. So here we use instead of using the time in the x-axis, we use the depth of discharge. And so what is this telling us?
Well, it's showing us that the unclean terminals have a much higher change in temperature, and then it kind of stabilizes at its highest level for most of the test, where the BMS is reducing the allowable discharge current. And it takes much longer for the cleaned or greased terminals to really reach that final temperature, and that's only towards the end of the test.
Is it fair to say maybe that this here seems to be a true representation of, you know, the internal cell heating after cleaning the contacts, whereas this here is showing much more the heat generated at the contact, which is then heating up quickly, cooling, and only towards the end it is actually, because the current levels are decreasing here significantly, it is then showing more the internal temperature when we let it cool down a little bit.
Yes, that seems a fair conclusion looking at this data.
So what would this mean if you use this sort of setup in your car? Let's say if you use a good BMS that allows you to limit discharge currents on temperature and to adjust the levels, that means you could decide whether you want a lot of performance and not such a long life, or whether you want less performance and a long lifetime. And if you clean the contacts, that means you can virtually discharge. I mean, for example, if we set the temperature limit to 55, which is what the manufacturer recommends, we are never reaching this after cleaning the contacts. So we would have been able to get full performance for the whole entire discharge of the battery. We just choose to start limiting the power at already 45 degrees centigrade. This is why we are kicking in with a reduction at this level. Whereas if you let's say if you don't use a BMS, then you don't know what's going on, and what might happen is that your batteries are getting really hot, which will decrease the life of the battery. But in any case, it's a good idea to clean the contacts and to grease them so that they don't corrode. So this was it for today with our cell connection optimization tests. I say thank you very much for your time. I hope you found it useful. There will be more videos and more information on our website soon, so check out www.REAPsystems.co.uk. There is a newsletter you can sign up to. I promise we will not spam you with anything you won't find interesting, so we'll just let you know about new videos or new information that we are putting up on the website. Also, as I said, we will be launching new products which will be easier to integrate and easier to use. So we are working more and more towards plug and play. And otherwise, I say thank you again and goodbye.